Hello everyone, welcome to Mechanical Software Education channel. In this video you are going to learn about a non-linear buckling analysis of a slender column by using Ansys. Look at this drawing. So a slender column is placed on the ground. It is in a vertical direction, that's why the name called as column. The entire height of this column is given as 1000 millimeter, and here the base is fixed, and in the top of the region the load is acting in x direction. In the negative side it is 250 Newton, and in a downward direction it is 500 Newton, and the cross section of this slender column is given as square cross section, and the dimensions for this cross section is b and h. Both the values are same. It is a square, that's why they gave us 10 and 10 mm, and the next input for this problem is Young's modulus value, that is 2E5 Newton per mm square, and the Poisson's ratio is 0.3. So before we enter into this problem, so we need to know what is meant by nonlinear and what is meant by buckling. So nonlinear is nothing but it is just a term just used in statistics to describe a situation where there is not a straight line or a direct relationship between an independent variable and a dependent variable. Okay, so now we just move on to this buckling. It is nothing but a sudden change in shape, that is a deformation of a structural component under this type of loads, such as bowing of a column under compression. So mainly while compression takes place, this buckling happens. Okay, with the help of these data, we can easily draw the slender column with the help of Ansys. Let me move on to Ansys. Let's start with the preference structure, and then preprocessor, you just start with the element type, add your element, and I just chose a beam 3 node 189 because it is a non-linear problem, so that's why I just chose this quadratic element. And now I just chose the material properties, go to material models, structural, linear, elastic, isotropic, and just give 2E5 0.3 as the Poisson's ratio. Then go to section, beam, common sections, so give the breadth and height as 10 and 10, and go to this preview, it is a square cross section. Then make your model of this beam, create key points, inactive coordinate system. The first coordinate system or the first key point should be at the origin. Give apply second key point. The entire height of this column is 1000, so give in y direction, give OK. So now you just go to lines and straight line. You can join the first point, key point, and the second key point with the help of this line. And now go to meshing, size control, manual size, lines, pick all the lines. I just divide this single line into 100 equal divisions. Okay, now give OK, and now go back and just give mesh and select this line, pick all the line. The entire line was meshed. Now just go to the solution, and you need to go for define loads, apply the load because the base is fixed in the displacement key points. Select the base part, and it should be of all degrees of freedom. And now you need to give some forces in the second key point. Select the second key point and give the force in the x direction. It should be of minus 250, and give apply, and select the same key point, and the next load which should be acting in downward direction as minus 500, and give OK. So here two loads which is acting in the second key point. One is in a downward direction and another one is left hand side. It should be of opposite side, like an you have x and y loads acting in the same key point. Okay, so now we need to solve this problem if we solve directly, we just solve this problem, means it should be like a static analysis. Actually it is an example of this static analysis. Buckling, mainly this buckling shows that it should be for Euler buckling effect, or even what about the next configuration? What we are going to use is to change the solution in control. So here this new analysis, you can check the entire concept of this analysis type is static, because it is a nonlinear analysis. We just use static analysis for finding this buckling load. And just go to this solution and controls. You can go for analysis option. So this is default a static analysis, that is a small displacement static. It should be mainly focusing on the linear analysis. So just change it to large displacement static analysis. So this is mainly focusing on the non-linear analysis. So now we just go for number of steps, because this iteration concept for non-linear analysis, we need to give this sub-steps. It is mainly this numbers that we are giving, number of substeps, maximum number of substeps, and minimum number of substeps. Now this is your choice, so it depends on your system capacity, and also the value you need to get. You can give the number of substeps as 20, and now I am going to give the maximum number of substeps as 1000 here. And the minimum value is given as 1. So just start with the 1, and the maximum number is 1000, and each and every steps we need to go for a number of substeps should be of 20. Okay, so here you just go for this frequency. In this frequency, just give write every substep. You need to give every substep here, because each and every substep should be calculating in this region. And now we just go for a nonlinear, and in each and every line you need to calculate the results. So on this program chosen, mainly the program chosen must be of Newton-Raphson. It is the best convergence techniques which we are using in this Ansys. And the maximum number of iterations we can give as 1000 here. And now go to the basics. So you can now check this large displacement statics. Actually while we are choosing the non-linear material, the models are a large strain elastoplasticity, and hyper elasticity should be there. It is nothing but the rubber and also the plastic materials. So with the help of the mode level, we can easily find this kind of answers with the help of this large displacement statics. Okay, so now give okay with these steps in the basics, and also this non-linear. We can completed. We already completed. All the others should be remain same, and give okay here. And now solve this problem. Current load step. Just wait to converge. Normally the convergence we already know. It is a main concept of finite element analysis, and for this non-linearity problem, we cannot solve it manually or directly, so we need an iteration method. So we normally know this iteration method. That's I already told that that is a Newton-Raphson method, and it is the main convergence technique to solve this problem. Look at this graph. It is already converged. Converged is nothing but the it is just to tend to meet at a point. So almost before 80th iteration point, the entire solution was done. Here you just see this, the in x-axis you can see the iteration numbers, and also even the y-axis you can see the convergence norm. Actually in the right hand side you can see the F CRIT and FL2, U CRIT, U INF, M CRIT, M L2. So the meaning for this is nothing but F stands for force, and U stands for displacement, and M stands for moment. So the force, displacement and moment which is acting in the particular convergence limit. Okay, so this is nothing but this is a force convergence criteria value for force, and also this FL2, this is nothing but the vector norm of the forces. Actually this is nothing but a disequilibrium concept, and also CRIT, it is nothing but CRIT is nothing but criteria. It is the convergence criteria for displacement. Okay, so this is also a vector norm of the displacement, and M stands for the moment convergence criteria value, and here this ML2 stands for the vector norm of the moment. So this is the explanation for this convergence. Actually after completing these steps, after solving these steps, we just check your results. Go to general post processor. You can read results, can by pick. So here the time sets for this problem we just set from 1 to 10. Okay, so if you want to check the results from 1, we can pick, or randomly you can pick 7 and you can get the answers. Okay, normally what we are going to do is first set. We can start with the first set, and you can go to the deform shape first, go to deformed and undeformed, and give OK. So now go to style, size and shape, and on your okay, this is the exact cross section, and now this is the first step. Actually if you want to read the second step or second set of reading, plot results, go to the deform shape, and you can see the mode shape. The first mode shape should be almost closer to the normal base structure, and we can pick for 7th step. Actually this is a step we just going for reading our result, set number 7. Go to read, and now go to plot results, deform shape. You can check the 7th step here. So if you want to check the final results for this Slender column, you can go for last set and read your results in deform shape here. Okay, so this is the exact drawing for this buckling analysis. Okay, this is a non-linear buckling analysis. If you want to read the results for fifth one, and you can check the deform shape, and now we can go for animate deform shape, how it get animated for deformed and undeformed shape. So you can check this is for the 5th substep. The maximum value is 338.064 millimeters. Okay, now we need to go for the next one, plot results, contour plots, nodal solution, degrees of freedom. If you want to check with the x component displacement value, you can check, or otherwise y value or z value, or this is the combination of x, y, z, the displacement vector sum. So this is the exact value for the 5th step. This is the 5th substep. So if you want to get your exact reading in terms of result, like drawing a graph, you just add your data. Normally it should be in a nodal solution, degrees of freedom. I just start with the x component displacement and give OK, and we need to pick the last or the second key point, so give OK here. And now I just add one more detail about y direction, and with the same key point I just click and give OK. It should be created in the time history variables, and just add one more as your z displacement and pick the second key point, so give OK. So now I need to go for the z combination first. So if you select this z combination and give the graph detail or graph data, you can check the entire time which happens in the x-axis, that is 0 to 1. The normally the iteration should be started in this region 0. The iteration is common for up to 0.07. Then the strain displacement is just started in this region, and it just go up to some height for the ending of the time number 1. Okay, so this is for the Z direction, and for Y direction you can see here. So just a drop, sudden drop. It should be of a deflection versus time, and with your Y direction graph, it is almost look like your X direction value. So deflection versus time graph, you can get it from this time history variable. Okay, so hope you can understand this, guys. If you really enjoyed this video, you can subscribe my channel and just support me. If you gain more knowledge through this video, just press like and comment. Thank you very much.